Hello, welcome to Introduction to Pandas for Time Series Analysis. This is a tutorial that I'm going to be going over. As an example, I'm going to use financial data, but there's going to be times during this tutorial where I won't be, just to illustrate a quicker point. So here, basically, we've got the packages that are pretty useful. Obviously, Pandas, um, NumPy, Y-Finance, Stats Models, Matplotlib. So we load it. And here I have an input for tickers for stock prices. So I'm going to put in Apple, Amazon. Then I'll put 2020. Actually, I'll put in earlier. And then I'll put in 2025, 04, 17, today's date. So I've got all my parameters set up. I mean, this is useful to do in the beginning of your code because this information, you could basically have it carried through, right? Different parts of your workflow. Okay, so this is very useful setting up parameters that you've already know that you're going to use. Okay, I mean, except maybe for machine learning, but we'll get to that. Now, what's also important is basically building checks into your data workflow. So I use things like if stock is empty, okay, if there's a missing values for a particular stock, then it's going to raise a value error. And then I use reset index, right? Because the columns are not, they come out in a way that you can't manipulate it. So when you reset the index, the columns become flat. And here's the stock returns a percentage change. Okay, so if I run this, I get all this information. Okay. Now there's a datetime 64 NS, and this is a datetime object. Okay, so which is pretty important. The NS means basically nanoseconds, right? And it refers to the precision and resolution of the datetime values in pandas, okay, and NumPy actually. So the datetime 64 is used to represent dates and times. It represents the nanoseconds. Now there are different time units, but Python and pandas by default gives you the nanoseconds, all right? Because it's the most precise, all right? Now, there's also something like where, taking percentage change is actually pretty obvious because we want to know the return on the stock. Okay, so intuitively speaking, that's pretty obvious. But then there's also something called taking a difference. Okay. Um, when we take a difference, we're basically normalizing the data, making it something called stationary. Okay, so you could see that like there's this trend. Basically, what the difference does is it detrends it and makes it stationary. Stationary meaning that it's bound. There's a boundary here. Okay, let me illustrate this point. There's a boundary. Okay, and this line will basically mean revert. Okay, to some level. Okay, so the behavior is predictable here. Okay, whereas this it could wander off increasingly forever. Okay, but this has a boundary, and that's why in time series analysis, basically you want it to be stationary because there's a predictable behavior to it. And we'll see the use of differencing later on with the ARIMA models. Okay. So like I said, there's a percentage change, which we use this command. Okay. And then there's that difference here, dot diff. Okay. So here we've got the the whole data frame. Okay. And that what I meant by reset index, the date becomes one of the columns. Okay. It's not like on the index column. Okay. Now there's also shift operators, which are very important. Okay. Um, we could shift it forward, this value forward. So this 72.09 becomes um, the second value. And then we could also shift it backwards. Okay. Where this value becomes this value. Okay. The reason why backward shift is kind of useful in my view is that like we could use past values to try to predict future values. Okay, so if we have this value, we could try to use that value to predict this value as a feature or as on itself. Okay. There's also slicing data, which is important in pandas, right? So we could slice it by the exact day, by month, and by year. So if I run this, we could see by year. Okay. All of 2022. Okay. It contains all of 22. Um, by month. This is all from 2022 to 2020. I think it goes beyond that, but it's all months, right? So we see, no, actually it doesn't. One second. So it will give you every day of the month. So when you slice it, it's like if you slice it by month, it'll still pick up every day. And same with year and same with day. Okay. It'll pick up every day of the year. Later on, we're gonna show something called resampling where you can pick up the monthly frequency. So that's the way you would slice data. Now we're gonna visualize some basic time series, some simple time series here. Here's Apple stock. I mean, basically we just use plot and then you've got these fixed size options, okay, to make it bigger or smaller, depending on your preference. So, I mean, if I wanted to make it smaller here, I could just do this. Oh no, what did I do? So I had to rerun the previous data set because it was picking up the one that I didn't want. So, but in any case, here's the smaller version, okay, of the graph for Apple stock. Okay. This is I mean, this is a question of aesthetics, right? Like you want your notebook or your presentation to look appealing to the individual that you're trying to present to. So, and here's two line graphs. I mean, you basically just stack the plots, but you've got this plot figure here. Okay. And then you could label it and then give it different colors and the line width. I mean, so it's basically, I mean, these two stocks are basically almost like tracking each other, right? Which is pretty interesting. I mean, it could be the influence of the market, right? The overall market movements that influence both of these stocks simultaneously. Here's a rolling average, okay, which is like basically a moving average window. You got this rolling function here with windows equal to 30 and then the mean. And it pretty much tracks, right? And in finance and trading, people make decisions based on like, if based on these moving averages, okay? If it develops a signal or not or whatnot. Now, there's also something that's pretty useful is to kind of track, it's to kind of track events, right? And see the influence of an event on the series, the time series. So, as an example, there's a key moment in May 2019 when the US increased tariffs on $200 billion worth of Chinese goods from 10 to 25%. Okay, I mean, this was a major escalation in the US-China trade war and affected market sentiment significantly. I mean, this was back in 2019 when Trump was president. Nowhere near the magnitude of the increase in tariffs as we see now today. But using basically these markers, we could kind of see the behavior of the stock pre and post. Okay. And we use this called ax.axv span. Okay. And it's useful for time series, right? In the sense that we could see the behavior pre-post. So we see that. I mean, we see in this area here that there's a huge decrease. I mean, it goes on for a couple of months until it started picking up again. Okay, and that could be due to, I don't know, alleviating the tariffs through some negotiation or whatnot. But we see this decrease here, which is pretty interesting. I mean, we could have done this for I could have done this for COVID, to see the impact of COVID. We could do it for numerous amount of things, but it's useful. Um, we could also try to examine a specific period. So like we were interested in this period and say we wanted to zoom in on this period, we could do something like this. Okay. And I mean like the major thing here is this matplotlib dates m dates. Okay. So we could take the weekday every Monday. Okay, so we're going to take data points every Monday. And this command mdates.weekday locator by weekday mdates equals to Monday. It's helpful because it gives your graph room. Okay, you don't want to plot every date. It's going to clutter up your graph. But if you take it every other week and you zoom in on a particular time period, it could be useful. Okay. And this B here is month. And this percentage D here is day. Okay. So you could see it jumps from week to week. And this would be every Monday. Okay. Yeah, I mean, and we see the decrease here, and then we see it at June 3rd. When we zoom in, um, the bounce back. From this graph, we couldn't tell if it's June, right? Because we're like kind of looking at it big picture wise almost. But if we zoom in, we could see it. Okay, so that's the usefulness of examining a specific period. It's like a subset, to get a feel for what's actually going on. So it's a m dates dot Monday is a constant in the matplotlib dates module that represent Monday as the day of the week. It's used to specify the weekday of which the major ticks of the x-axis should appear when using a weekday locator. Here's a kernel density plot of the prices. Okay. I call it typical prices here because I've averaged the high, the low, and the close, if you guys didn't catch that earlier on. And the reason why we would do something like that, I mean, in the context of finance anyway, is because we want an actual, like, a price that's truly reflective, okay, of what happened throughout the day versus what happened at the end of the day. Okay, so it's incorporating more information to make this price a more robust estimation of what it should be, the stock price should be. Yeah, I mean, we see a distribution here, right? I mean, like the fact that it goes above 70, 80 is a little bit unusual. A lot of it, the density falls between 30 and 50, right? Now we're going to be moving on to date range. And I have this table here to kind of show you what the parameters are that you could input. So we got the start, the end. I think the frequency is pretty important. Time zone setting, I think it's dependent on where you are. Okay. Normalize is equal to true, inclusive, and closed. Um, and then there are the calendar days where we've got daily, business days, Mondays, Fridays, no holidays, weekly, month end, month start, quarter, year end, year start. So there's a lot of parameters that you could use for specifying your date range. I'm going to use something simple at first. So this is daily data from 2020 to 2021, the end of 2021. We capture all that. Now look at the daytime. We see that it's in nanoseconds, capturing that level of precision. The length is 731 days. Um, and the frequency is daily. Now we've got hourly data, I mean, which is useful for e-commerce transactions or whatnot. And we could just see the hours. It goes up to, yeah, once it goes to 24, it resets to 0, if you can see this here. So it'll go up from 1 to 23, and then it resets at 24. Okay, which is the beginning of the next day. Here is business days. This is useful for, I guess, more like stock market analysis. Commodity futures, if you were like to look into those markets, they trade, I mean, I think like 6 days a week because they open on Sundays. So it's a little bit more difficult to get that. But I mean, like normal business days are pretty much common for the stock market. If you're like a e-commerce store owner, obviously you're open 24 hours a day, every day, right? So um, we could exclude specific holidays. Here we use something called custom pandas time series offsets custom business day, and then pandas.tseries.holiday import US federal holiday. Okay. And then we basically exclude holidays. Okay. So on as a check, January 2020, which was MLK Day, was excluded. Okay. And if we look at this here, there is no ML 120. Okay. Um, Time delta is a very useful function in time series analysis. You could see, like, you could create like a date and then basically a window, 10 days before, 10 days and after, um, the specific date of interest. And that's the usefulness of it, okay? Um, in a previous video, I showed something called event analysis, where we could kind of see a window where we see the stock price 10 days before, how it behaves, and then 10 days after. Okay, the stock market returns. Okay, so it's useful for that. One of the reasons why it's useful. So here we get 10 days after. and 10 days before, 416. This PD dot time delta, and you can specify the number of days here. Okay. PD to date time, you have to make it, you have to, if you have a string, you have to use this PD to date time function. Okay. Now we use the time delta. I mean, like I show another example here. Um, but this time we're using timestamp instead of to date time. And it'll give the whole hour, minutes, seconds range. Okay. This is probably a lot more useful for higher frequency time series. Amazon, I'm sure, like every second, like an order is being made. So, I mean, like when you work with data like that, you're going to probably want to use this timestamp type function. Okay. And then we could add 5 days to it, obviously, and see that. So here I give you accumulation, kind of a summary of using all three functions together, date range, timestamp, and time delta. So we start off with creating a set of dates, okay? Business days only. Then I create some random data here, like a synthetic data set, okay? And then a price, earnings date. I initialize an event flag. The earnings date is for, I mean, like stock announcements, right? We got it like I think like every quarter or so, right? So like what happens pre and post. Sometimes if a bad earnings announcement occurs, then the stock for a couple of days just goes down, right? And then maybe eventually it'll pick up. But the reason why these event analyses are kind of useful is because we get to see that, right? We get to see if there's an actually statistically significant um, impact. So we create this window with the date range here, right? Date minus PD time delta days is equal to 7 plus PD times PD time delta days equals to 7 plus, right? And then frequency is equal to business days. And we set flag 1 to within the window. Okay. Um, and then basically what will happen is that you'll get an event flag. Okay. If I subset it to equal to 1, we don't see it here. We'll get event flags for each of those, for all those dates. Okay. So I said timestamp is equal to February 2015. And you see that we see the days before and the days after. I mean, and sometimes it could have no impact, right? Sometimes like you're going to find that, that particular day, that event, it didn't have an impact on the prices or whatnot. Now you could use this for marketing studies as well, event analyses. Like you could see like, okay, did discount have a statistically significant effect on sales pre and post, right? I mean, these are things you could do in multiple domains, okay? So transforming a date string into an object, I mean, into a date. We could see the data types here. If we put this column of values, we get an object. And the idea is to transform it into datetime 64, and we do that by the datetime, which we saw earlier. Okay, and this would be the proper way of doing it, adding the date. We would do the brackets date is equal to PD to datetime, DF date string, and this adds that column. Okay. There's multiple ways to format this, right? you could do it by day, month, year. You could do it month, day, year, right? So there's multiple ways of formatting it, and it depends on what your, I guess, what your preference is, and then also the data that you're given, what format it comes in. Okay, so those are probably two of the factors. Okay, um, here I just formatted month, day, year. Okay, and we could see that the transformed date is 2025-04/16. Okay. I mean, you would think that it would come out in this format, but this is the way it comes out. And then the same with here. This is the day, month, year, and we get this. Okay, because of the input. The input is day, month, and year, and then we use the daytime and it transforms to this um, output. Okay, yeah, so I'm sorry, I just slipped up. So it is because of the input. Okay, so that influences how you would format it. Okay, so if you got this in this format, month, day, and year, you're gonna put it the format month, day, year, and then you're gonna get an output that's similar, year, month, and day. Okay, I apologize for that. And then here we're missing, like dealing with missing value, like how to handle missing value. Okay, this is a little bit of an exercise. Um, you're not going to get data that's clean up all the time, obviously. I mean, in Yahoo Finance and like some of these APIs that give us time series data, they pretty much have cleaned it, right? So if you're working with these APIs, it's pretty much good to go. There's going to be some cases though where if you're given a data set that they're going to have missing values, and that's just inevitable. Okay, so here we've got this original data frame where we've got these NANs. We do this forward fill. And we just fill it forward. I mean, if that makes any sense. So this one, the closest thing this NAN has is one. So it'll fill one. Same thing here, it'll be a one. Here, the closest thing is a four, so it'll fill to a four. Okay, and you see that one, 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 four, four, and then six. Okay. Here you can't forward fill because it's the first value, but you can forward fill to this one, which is a two, and this is a five. Okay, because it forward fills at five. And another quick note, the reason why you would want to do this, I mean, like, this is for easier data sets in the sense that, like, you know that there's going to be some kind of linear trend or some kind of constant trend. Okay, it would work under those circumstances. Okay, but if you find that it's very nonlinear, some like interpolation technique like this was, it'll probably be more harmful. Okay, if there's like a nonlinear patterns that are not captured by a constant increase in value or a constant linear or constant trend. Okay. Backward fill, it's the same idea except going backwards. So it's four, 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 right? Six, right? This will not be able to go backwards, but this can. So it's four, four, and then two, two. Okay. Now we're going to talk about time resampling. Now we could do these or resample by year end. So I've got this data here from 2019 to 2024. And then I do year end and I pick the first five values. Okay, so each year, 2019, 2020, 2021, 2023, we get the mean. And there's obviously an increase here. Same thing with monthly, okay? But it's going to go forward in that same year, right? So 131, 228, 331, 430, 531. This is the really good thing about Yahoo Finance. I mean, they'll give you the month ends, right? Like you don't really have to worry too much about things like that. As where you're creating your own data sets with PD date range, you have to worry about these uh these different days of the month and changes throughout the year. So that's something to keep mindful of. I mean, that's the kind of the tedium that you have to deal with when working with dates. Here's a weekly, so you can see it jumps 7 days. And here are all the options, I mean, for what I just showed you. Okay, so I mean, you've got monthly, weekly, weekly on Monday, daily, business day frequency, hourly frequency, minute frequency, second frequency. I mean, in general, most of us will not be working with this, but there are people, like I said, that work with high frequency trading and finance, um, e-commerce transactions, right? That have high transaction rates. I mean, these are the people that are probably going to be working with this pretty heavily, and they'll be interested in finding what kind of statistical distributions come out of that, whatnot, right? Because I mean, the idea of statistics is that, the more data you have, the more accurate your modeling estimates will be in general. So this is good to kind of know about. Okay. Now we're going to be talking about autocorrelation. This comes from the stats models package, but I think it's important to mention. Um, Here we again, when we do something like autocorrelation, it's good to transform the data, okay? Percentage change in this case, okay? If we're working with stock market data, definitely percentage change. And then we do this for Apple, the ACF and PACF returns, right? And you could see that, obviously the correlation on the zero lag is with itself is one. I mean, the correlation of the first lag with itself is one, right? But then we see the rest of it, it basically is bounded. Same with the PACF, okay? And we see that it's bounded, so it's basically stationary data, okay? There's very little serial correlation, okay? If we look at lag one is slightly positive, all the other lags hover near zero within the blue confidence interval. This means very little serial correlation. Today's return almost has no predictive power for future returns, okay? This supports like something called the efficient market hypothesis in finance, where price changes are basically random. So this is what this would exhibit. Okay, the PACF, the right plot, the lag one shows a small spike, but the ACF, um, but like the ACF, the rest are mostly inside of the confidence band. Okay, so there's no significant partial order correlation after lag one. There's no strong AR structure in the returns. Okay, autoregressive structure, which is the lag. And then you might model this as white noise or possibly a very low order ARIMA model, like ARIMA 00 or ARIMA 100 to check. ARIMA 000 is basically something called a random walk, where it just moves. I mean, this would be a random walk. You know, it could be multiplicative. I mean, which means that it'll increase. with some level of volatility, but in most cases, it's something called additive, which is another way of saying uh, a bounded series. So now we're going to be talking about seasonal decomposition, and I just talked about something called additive and multiplicative. Okay, so the goal is to break down time series into three components: a trend component, right, which is the underlying trend of the series; a seasonal component, right, the seasonal variations that repeat at regular intervals, and then the residual component, the noise of the random fluctuations that remain after removing the trend and seasonal. So here in the additive decomposition, basically it's what it means is that you're adding the components. Okay, the Y is the actual observed series, and then we're decomposing it into trend, seasonal, and residual. Now we could get the residuals by subtracting the trend and the seasonal from the actual series. And same with the multiplicative. Here, in some cases, in order to make a multiplicative series, we multiplicative series additive, we could take the logs. And usually log transforms are useful for that case because additive series are a lot more useful or practical to work with. Okay. Um, why? It's the same idea except it's multiplied. So the additive decomposition is useful when seasonal variation remains roughly constant over time. Okay. And multiplicative decomposition is better when seasonal variations grow or shrink with the magnitude of the data. One way to determine which model fits better is by inspecting the residuals after this decomposition. Like if the residuals are look approximately normal distributed, which means bounded, then the model is a better fit for the data. This is because the normal distribution in residuals suggests that the model has effectively captured the underlying patterns, leaving only random noise. So in the context of Apple stock prices, the multiplicative decomposition looks actually more normal. So if I look at Apple, we could see that we're extracting this is the actual values, right? We're extracting the trend, and this is the seasonal value, and this is the residual. You see that the residuals, okay? When we look at the residuals, we could see that they're bounded. I mean, like I was showing this earlier with the idea of stationary, but we could see that they're bounded, meaning it doesn't wander far off, right? It'll mean revert to some kind of average level, right? Or it will not wander so far off from the average level, okay? And that's important to know. Then you know the specification of your time series, okay? In the additive decomposition, we don't see this. We see my screen is freaking out here, but my we see this that it basically kind of widens, okay, this gap. And that's called something called there's a lot of terms for it. Non-constant variance is a good term in the residuals, like heteroscedasticity and econometrics. We basically see that it's increasing, right? It's not bounded by an average level. So the difference, additive decomposition assumes that the components, trend, seasonal, and residual add together. In multiplicative decomposition, it assumes that the components multiply together, and this works well when seasonal effects grow or shrink in proportion to the level of the trend. So another graph just to kind of drive the idea home. If we have this trend growing up, basically the seasonal will grow with the trend, the seasonal component. So that's how you know it's going to be multiplicative. In additive, the seasonality will not grow with the trend. It'll remain constant. Okay. So that's the point that this graph is trying to make. Now, answering the question finally, does Apple look like it's multiplicative or additive? I mean, you could kind of see that multiplicative decomposition was more suitable for the Apple stock price, right? Because inherently scaling of volatility and price fluctuations as prices rise, the magnitude of the fluctuations, including the seasonal effects, can increase, making the multiplicative model a better fit for financial time series data. So what that basically is saying is that, like I was showing you, kind of that multiplicative trend, um, the seasonality grows with the trend, but also we've got something called volatility, right? Where these huge magnitudes, this is the way a stock price probably behaves more um, than something like this, right? So these fluctuations basically magnify the possibility of an increase. Okay, so that would be what I would consider multiplicative versus additive, which is just a regular trend. Okay. There's going to be times when you're going to want to extract the components. For some reason, this didn't happen to me before, but we had to fill in some missing values, um, and we concatenate it. Okay, the seasonal trend, residual, actual values, and reconstructed values. Okay. Um, yeah, I'm not going to go into super detail about like, some of the I guess like the data hangups that could kind of occur with this. You usually should get basically a decomposition that has numbers in it. Okay, in my case, it didn't work out that way, so I had to do some manipulation. But the main idea is that we have these different components. Okay, that's kind of what I want, and they should technically add up. In some cases, they don't, but technically they should be equal. Okay. Um, Another point I want to make out is that, at times there are going to be um, there are going to be times when you want to model things separately. So like, you could use something like an autoregressive on the trend and you just want to predict the trend. You could use Facebook profit just on the trend component just to see the more more of what the trend is going to behave like, right? So you isolate these kind of components, you get a better sense of the underlying direction, right? You're isolating certain things that you want to know more about. Okay. Now we're at something called the random walk. And I would consider this kind of like a baseline model for anything that could kind of occur because in time series, you could make assumptions in the sense that like, okay, I think there's going to be, some medium general growth or whatnot. But random walk is kind of I would say a baseline idea of like how a time series would behave, right? Like you don't know, you're not able to forecast the future perfectly, obviously, but a random walk kind of gives a description of like basically zero information as to like what you think is going to occur. Anything could happen. Okay. And this is like a random walk series. And again, I make the point of differencing data. Okay, this dot diff here. Because if you want to work with something like where you don't know about, you want to a lot of the models that we have, okay, if it's random walk data, a lot of the models that we have, it assumes some type of normality, okay. So that's the first difference of a random walk. And obviously the random walk pattern, we could see that it's downward trending, but I mean, if we were to simulate this and run multiple, it could be going up, We could have things that go up. It just depends, right? But we want to work with the point being that we want to work with data like this, okay? That's somewhat bounded. I mean, you're going to have your occasional things that are not bounded here, but you could see that this is not bounded. I mean, there's definitely some kind of thing going on here, right? So that's the idea of a random walk. I mean, this is useful in finance. It's used a lot in finance, but I've also seen it used in predicting things like cloud capacity, right? On a daily level, because you don't know what kind of data is going to come in on a daily level. Now we're going to go into basic time series modeling. Um, don't be scared by the mathematics. I don't think it's something that you need to know, especially in this day and age where we've got functions that do most of the work for us. But here, ARIMA is a foundational model. It's called, autoregressive integrated moving average. That's the full name. So this is the autoregressive part, and this is the moving average part, right? Um, this P is the autoregressive, the lag. Q is the lag for the moving average. Okay. And D is the order of differencing. And we're always going to want to difference it like a one difference. If you saw earlier that if it's 0, 0, 0, it's a random walk that's not bounded, okay? I mean, we could do 0, 1, 0, and that could be a random walk where we have it differenced at least. So it's written in this way. These are like something called backshift operators. Okay. These are the autoregressive components, and this is the moving average. And E is the white noise. This is always the error, or they're going to call it white noise. Okay. Depending on who you talk to, what camp of time series people you talk to. I mean, there's econometricians, there's statisticians. Um, but I mean, this formulation is generally agreed upon by everybody. So the regressive and the moving average and the white noise. Okay. Before we actually use the ARIMA model, we're going to probably want to do a hypothesis test on the time series. Now, in financial markets, most of them, that you're going to have the difference, but there are other time series that you might not be familiar, well, I might not be familiar with. And a good thing to do is run something called an augmented Dickey-Fuller test, and it checks for stationarity in the time series. Okay. So remember the definition of stationary, it's basically a bounded, right? We want the error term bounded. You could say the same thing for additive. The two are not the same, but they're similarities in ideas, okay? So we try to test the hypothesis by taking the first difference. T is the time trend, K is the number of lag differences, and ET is white noise, okay? And the null hypothesis is that the series has a unit root and the lambda is equal to 0. Rejecting the null hypothesis for stationarity. Now, in time series, if like, I mean, statistical inference in general has like a bunch of hypothesis tests, like t-test, normality test, and whatnot. Time series also does, and this is one of them. There are multiple hypothesis tests for time series. But for the sake of this tutorial, I'm just going to be talking about the augmented Dickey-Fuller. Now, if you look at the code here, I'm basically pulling the data I plot it, and then I check the stationarity, right? If it's greater than point, if the p-value is greater than 0.05, it's non-stationary. Okay. So the original series, I'm checking if it's stationary, and we saw in Apple later that it's not. I mean, the that's the obvious answer after some of the sections that we saw, right? Um, then we take the first difference, we recheck the stationary after the differencing, and then finally we fit an ARIMA of 111, a basic model, right? Using stats models here. And stats models also has augmented Dickey-Fuller. Now, there are ARIMA functions out there that basically automate this thing for you, where it'll find the optimal autoregressive term, optimal differencing term, optimal moving average term, right? Based on something called the Akikai information criterion, which is it's a likelihood function, right? So you're optimizing parameters. It's a lot similar to what you do in machine learning with grid search. You try to optimize parameters that will not overgeneralize or undergeneralize. ARIMA has its own version. For the sake of this tutorial, I won't be discussing that function. But in any case, we see the Apple raw stock price here. It's going up, right? And we see this here, right? It's not stationary. Our stationary test, it fails it. Okay. 0.526, that it doesn't work out. It doesn't work out that it's stationary. Okay. But then we take the difference and then look at the difference p-value. It is stationary. Okay. Then we get the outlook. I mean, some output for this function. We could pretty much see that, these aren't that great. I mean, these are the first two that I would look at. They're not statistically significant. Here's the Akikai information criteria where it optimized it. Okay. And like I said, there's a lot of other tests here for time series, which I will not go into. You've got the Lejung box, Jock-Bara, skew, and kurtosis, which everybody should know if they know basic statistics. Heteroscedasticity and whatnot. Okay. So that was a simple formulation of a time series model, like what you would want to do um, to model your first time series, right? You want to check if you even need to difference it. Okay. If it's stationary, if the data is stationary at that point, you're pretty much good to go, and you wouldn't even need to difference. If you do difference it, it'd be like a second order difference. It might affect your results. Um, and there are methods for that, but for the sake of this tutorial, I won't go into that. Now, finally, we're going to be talking about feature engineering time series, and then also putting it into a simple machine learning model. You could manufacture features from a simple date, right? Which is pretty amazing, right? So here in Apple, we've got the date, I could extract the year, month, day, the day of the week, the day of the month, the week of the year, quarter. Is it a weekend? Is it a month start? Is it a month end? Okay, so there's multiple features. I mean, sometimes like people manufacture features without knowing actually kind of the implications of it. I'm guilty of that as well. But the thing is that we're not really looking, like sometimes we are looking for intuition. I think that would be more helpful. But sometimes we're just looking for kind of what do you call it? Results, right? Based on feature engineering. I mean, like, some people, I guess in machine learning, one of the blind spots in machine learning is we're just optimizing for metrics, right? Like whether our mean squared error is low. Um, and we're going to put in a bunch of things that maybe we have partial understanding of. But I mean, in these features here, for the things that I would understand is like, say, for is weekend. Maybe for is weekend, Friday and Saturday, if you're a retail business, your result that'll significantly impact your results, your sales results, right? So putting in data for is weekend, like a flag, whether it's Friday or Saturday, that will be helpful. Maybe the day of the month of the year, right? Or several months of the year, right? Or the quarter of the year, right? The last quarter of the year, you could expect holiday sales or whatnot, right? We could put a holiday sales flag in it as well. These are all time series features that we could use to predict how well our target variable would be looking for, okay? And then we could create lag variables, which I mentioned previously with a shift one, moving averages, okay? That could be predictive of a 7-day and 30-day, right? So here we basically get the features, and then we take the close, a backward shift, okay, because we want that to be predictive, right, of the forward of the target variable, right? So t, so I mean, t minus one, right, should be predictive of yt, right? So that's kind of like what I'm trying to get at, that idea. And we run the machine learning model, right? We drop the last row in X, we drop the NaN values in Y. We sequentially split the data. There should be no shuffling. That's an important point to make. I think the most important point. We've got something in scikit-learn called train test split, and that shuffles the data, okay? We want to keep the sequence preserved. It's not IID, independent and identically distributed, but the values are correlated. So you don't want to shuffle the data. You have to create the split yourself, right? So if I fit it and I go through kind of the standard machine workflow, right? I initialize the model, I fit the train, X train and the Y train, and then I predict the X test and I get the error. 19, which is, I mean, it could be, it's bad actually because of this, our stock price is not that high. It goes to 160 or 170, right? But there's multiple ways that you could do, like after that, if you check and you're not happy with the MSE, you could go back into the earlier part of the workflow, the feature engineering part, and add more. I mean, this is all, I think, dependent on your creativity level, okay, and how you optimize the features. So that was the whole tutorial on pandas for time series. As an introduction. There's a lot more, but hopefully you learned something. And thank you very much. And I hope to see you in the next video.